Hello everyone. Now, based on whatever we have studied in our previous lecture, that means like we have studied in a previous lecture different kind of flip-flops, RS flip-flop, JK flip-flop, D flip-flop. Based on them, we'll try to see how we can utilize them to create different kind of utilities. The first thing is that can we convert? So can we use one flip-flop to design another? So let's say we have SR flip-flop. We know that from SR flip-flop we can design D flip-flop. But can we design JK flip-flop or T flip-flop using D flip-flop? Or basically one flip-flop from any other flip-flop. Then in this lecture we will also see that how these flip-flops, let's say D flip-flop, how it can be used to design clock divider, counters or sequence generators. The idea of this lecture is that various applications where these flip-flop can be used, and a rest is left onto imagination that where all we can use these flip-flops or memory elements. More particularly synchronous flip-flops. So let's say we would like to design a JK flip-flop from a D flip-flop. From the theory of JK flip-flop, we know that this is the truth table of JK flip-flop, that when J and K both are 0, Q plus means the next state of the Q will be same as the previous Q. If J is 0, K is 1, next state is always 0 independent of the previous state. When J is 1, K is 0, the next state is 1 irrespective of whatever was the previous state. When J and K both are 1, then the next state is inverse of whatever was the previous one. So if Q was 0, then Q plus next state of Q is going to be 1. If it was 1, then next state is going to be 0. So we can write all of these in form of we can solve a K map, and we can see that Q plus can also be written as J Q dash plus K dash Q. Now we would like to design this JK flip-flop using a D flip-flop. So D flip-flop is a delay flip-flop. Whatever is the input of D, that would be represented by Q at the active edge of the clock. So we can also write that Q plus is equal to D for D flip-flop. Now if this is so, then we can replace this Q plus, this we can, whatever is the value of this J Q dash plus K dash Q, we can assign it to D, and then essentially this whole system will work like a JK flip-flop. So if I take J and K as an input and provide this J and K dash as an input to this NAND gates, and Q and Q dash I connected from this output of my D flip-flop, then essentially this whole system represents a JK flip-flop. Although underneath I'm using D flip-flop, but the functionality of this whole circuit, so if I say that this become the complete circuit where J and K is the input, another input is the clock, and the output is Q and Q dash, then this system is actually a JK flip-flop. Similarly, by looking at the characteristic equations of two flip-flops, then we can think of designing any flip-flop from the other flip-flop. Okay, so this is one of the interesting application of our like flip-flops, that once we have one, then we can also drive the other one. Now let's look at the other application. So can we design a clock divider using D flip-flop? So rather than looking at, so this is my D flip-flop. So rather than looking at design, what I'm trying to show you is the direct implementation. Then we can analyze that how it is working. So if this is the this is my D flip-flop, And I know that whenever clock, so whatever is the given the clock, positive edge of the clock, this D would be transferred to Q. So if I make sure that at every clock edge my D is the alternate 0 and 1, 0 and 1, then this will make a new clock which would be half the frequency. So for that, what I need to do is, because if D is whatever is the Q is actually equal to D, but Q dash is equal to naught of D. So that means if I can connect this Q dash to D, so then I would have an alternative positive and negative values at the value at output Q. So let's understand it with so basically I'm connecting this Q dash with the D. So let's understand it with this clock signal. So with the input clock waveforms. So let's say this is my regular clock. Now at the regular clock, let's say initial output was 0. So if initial output was 0, then Q dash is going to be 1 all the time. And if it is 1, then at the positive edge of this clock, the next output is going to be 1. And for how long it will remain 1? It will remain 1 for whole 1 clock duration. Similarly, at this moment when Q was 1, Q dash was 0. Because Q dash was 0, at the next positive edge, the output Q will become 0. So this way my Q would keep on alternating, and it also looks like a clock signal, but of half the frequency or double the clock period. So in this way, my D flip flop can be effectively utilized to form as a frequency divider. Here we have seen it can be used to divide the frequency by 2. So whatever is the clock frequency, the output Q here represent clock frequency f by 2, or the time period is a double of previous time period. Duty cycle is in this case it is same 50%. So whatever is the whatever is the duty cycle of initial clock, it does not matter, but the duty cycle of Q is always going to be 50%, because they are like it is half, it is low for 1 clock period and again high for 1 clock period. So the duty cycle is independent of the previous clock and is always 50% in this case. Can we further divide it? So can we divide it by any particular frequency? So for that I can repeat this circuit. Yeah, so one more thing, that I can also design this clock divider by using T flip-flop. In case of T flip-flop, we know that if T is 0, then output remain as the previous state, but if T is 1, output keep on alternating. So instead of a D flip-flop, if I have a T flip-flop, in T flip-flop I can always give this T as 1, then output will keep on fluctuating between 1 and 0 after alternate clock cycle. So that means T flip-flop can also be used for clock division. Yeah. Okay. So can we divide it by more than value of 2? Yes. So for that I can repeat this circuit. So because of this one circuit, my output is clock by 2. Now if I give this clock by 2 as a input to next D flip-flop, so I connect this Q to next clock, and then the output is going to be clock by 4. So similarly I can connect it further. I can further connect it, and then I can say that this output will go as an input clock for the another D flip-flop. So then this output signal is going to be clock by 8. So this way we can keep on doing it recursively to essentially achieve at whatever division we would like to make. So let's say I would like to divide clock by 1024, then I would require 10 such flip-flops. Each of them, for each flip-flop the circuit is going to be same, or I can use all the T flip-flops where T value is 1, but the output is connected as a clock to the next cascaded flip-flop. So here output is connected to the clock of next cascaded flip-flop. So this could be a interesting efficient design where the circuit is very minimal. I just required T flip-flops and direct connections, no other gate essentially. But there is one major bottleneck or major issue with this particular clock divider circuit, that all the clocks, all the generated clocks, for example, this clock, this clock, this clock, so all of these clocks are not synchronized. So that means that all these clocks will not be going from low to high at same time. And you remember that the reason that we are using clock is because we would like to have a synchronous circuit. Because we would like to have synchronous circuits, then all the clock transitions should happen at same time. But here, this clock and this clock would be delayed by a propagation delay of this D flip-flop. Similarly, this clock and this clock would have a timing difference of a propagation delay. So because all of this become asynchronous clocks, so that may not be a very good idea to have a asynchronous clock. So we'll try to see some other mechanism to make a clock division which is synchronous in nature and which can still be efficient, or we can still able to achieve a clock division using these flip-flops, any of these flip-flop, D flip-flop or JK flip-flop, etc. Okay, so this is how we can do clock division. Now let's come to counting. Now, what is a counting? So basically, let's say in one of the clock period, first clock period, the output is 0, 0, 0, 0. The next clock period, output should be 0, 0, 1. Then 2, then 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, and 15. So this counting could be anything. And this counting is a very important digital circuit in the sense that it can help us to count number of clock cycles. And as we have discussed in one of the previous lecture, that this clock period define how much work can be done within clock period. So that's how we can have a good estimate of time. Also, these counters can also work like a timers, and they can help us in counting the time based on the counter. The value of counter in that case could be huge. So it could be 15-bit counter, 12-bit counter, 30-bit counter, whatever. Okay, so if you look closely at these values, what you will see that this is the least significant bit. This least significant bit will keep on alternating every after every number. Okay, so this becomes 0, this becomes 1, and similarly you can say this is 0, 1, 0, 1, 0, 1. So this is every alternate number become every next number is the inverse of the first one. So I can say this is again looking like a 1-bit counter. Okay, it's a 2-bit counter. Now let's look at the second bit, or basically 2's place bit. In case of 2's place, I see 0, 0 2 times, and then I see 1, 1 2 times, then again 0, 0 2 times, 1, 1 2 times, so on and so forth. So basically the frequency of 0 has got doubled. Okay, and similarly frequency of 1 has got doubled, and it's all looking like a clock signal itself. Similarly, for the third bit, we see 4 zeros together and then 4 ones together, then again 4 zeros together, then again 4 ones together. And for the fourth bit, we see that we have 8 zeros together and then 8 ones together. So essentially, it looks like a clock signal. Okay, so the other observation is, yes, frequency of every bit is half from the other. So in this way, we can use a clock divider circuit. So this could be, if I see my previous if I see this circuit, so basically this could be clock by 2 could be the first bit, clock by 4 could be the second bit, and clock by 8 could be the third bit. And this way we can have another D flip flop to have fourth bit. So my simple asynchronous clock divider can also work like a counter. Now, every time we are using the output of a D flip flop as a clock input to the next flip flop. But as I said earlier, this would be a asynchronous counter because the counting values will not be synchronous with respect to clock. My clock is changing in new flip flop, in a different flip flop. All the values are changing with respect to their own clock, their own time. So yes, but the message here is yes, we can use these clock divider also as a counter. And the other in the other way around also, that we can use counters as a clock divider circuit as well. So the challenge with the asynchronous counter, both asynchronous counter as well as asynchronous clock divider, is that my clock is asynchronous, my outputs are changing asynchronously. So how shall we design a synchronous counter or a synchronous clock divider circuit? So if I want to do anything synchronous, that means I am not supposed to connect any input to my clock. My clock should be connected to only the global clock. So clock should not be modified at all. Now, how should I design a synchronous counter? So for that, if I create a state table, I say that this is the present input, then what would be the next input? So based on that combination, then I can create a K-map for all the next states, and then we can create a counter. So to illustrate this particular point, let us try to design a 3-bit synchronous counter. So in 3-bit synchronous counter, if my present state is 0, 0, 0, then the next state, so what is the next state? Next state means after the positive edge of the clock, then the next state should become 001. Similarly, if the present state is 001, the next state after the clock edge should become 010. If the present state is 010, the next state should become 011, and then 100, then 101, 110, 111, and after the input is 111, it should again go back to 000, because it's a 3-bit counter. So after 7, it has to come back to 0. So how do we solve this? Now, what should we go? What should we do ahead? Next thing. So we know that whatever we would like to have as the output, if we give that as an input to my D in a D flip flop, if I give that as an input to D, then that will become that would be transported out, that would be given as the output in the next state. So whenever the clock positive edge of the clock will come, that D would become Q0 plus. Similarly, for this flip flops, I would require a 3 flip flops again. I would require 3 D flip flops. For each flip flop, this Q0 plus value, I can say this is actually the D value or the input value of that particular flip flop. So similarly, whatever I would like to have the next state, if that is the actually the input of that particular flip flop. So so we would like to create to know what are the logic expression for Q0 plus, Q1 plus, and Q2 plus, and then that we know already that we need to solve our K map for these 3 inputs, Q0, Q1, and Q2. So here I have sold this K-map directly. Then you can work out yourself, or maybe you can quickly see that this Q0 plus. So every time Q0 is 0, then it becomes 1. This at whenever this is 1, it will become 0, irrespective of Q1 and Q2. So that means Q0 plus is equal to Q0 dash. Similarly, Q1 plus, it is 1 only in these two circumstances. That means Q1 dash Q0 or Q1 Q0 dash, which is also an XOR operation. Okay, so here also this is 1, but the condition is similar, that it is Q1 dash Q0 or Q1 Q0 dash. For Q2 plus, we see it is 1 for these four cases. The first case is Q2 dash and Q1 Q0, or it is Q2 and Q1 dash plus Q0 dash. Okay, so this whole could be combined as Q1 dash plus Q0 dash. So if I would like to design a synchronous counter, then as I said, so if this should be the input of this D flip flops. So I can say that D0 would be equal to Q0 dash, D1 is equal to Q1 XOR Q0, and D2, I can simplify this equation as Q2 XOR Q1 Q0. And I can implement this using these three D flip flops, where D0 is equal to Q0 dash, and D1 is equal to Q1 and Q0's XOR, and D2 is equal to XOR of Q2 and of Q1 and Q0. So this implementation can help us in doing a synchronous 3-bit counter. So as you say, it is synchronous. That essentially means that all the values of Q0, Q1 and Q2, they would be available at the same time, equal to propagation delay of these D flip-flop. So after a clock period, so whenever the active edge of the clock, let's say it's a positive active edge. So as soon as positive active edge of the clock will come, after propagation delay, Q0, Q1 and Q2 would be available as the output. So they are called synchronous outputs or synchronous counters. Now let's say this was a 3-bit flip-flop which was counting from 0, 1, 2, 3, 4, 5, 6, 7. Let's say I don't want to count from 0 to 7, but I just wanted to count from let's say only 0 to 5, 0, 1, 2, 3, 4, 5, and whenever 5 will come, I'll go back to 0, 0, 0. So what would happen if my input is 1, 1, 0, 1, 1, 1? Both of these inputs are invalid, because if counter will start at 0, these values will never come. So as soon as 0, 0, 0, 0, 1, 2, 3, 4 and 5, from 5 it will go back to 0. So that means these input combinations will never ever come. So the same technique, same method we can use. Same technique and same method we can use to design this 5-bit modulo counter. This is called modulo because it again, after 5, it again go back to 0. So similarly, there could be if it's a modulo 12 counter, so that means after 12 it will again go back to 0. Okay, so I should have said modulo 5 counter. The bit is not required, so it's a modulo 5 counter. Now to solve this, again we have to write K-maps, and K-map for Q0 plus, Q1 plus and Q2 plus. Now we can try to take advantage of this don't care condition wherever it is possible, and then we can see that Q0 plus would again be equal to Q0 dash, and Q1 plus. So this Q1 plus, these are the two values of where Q1 is plus. So Q1 plus is 1, So one of the value would be happening when Q2 is 0, Q1 is 0 and Q0 is 1. The other we can combine with a don't care condition, so it will become Q1 and Q0 dash. Similarly for Q2 dash plus, again we can create a truth table, and truth table is there, so we can create a K-map and then can optimize it. So in this case I have solved it, it become Q1 Q0 plus Q2 Q0 dash. So this is how we can design any modulo counter. So you see one more thing here, that this modulo 5 counter can also be used to design divide clock division by 6 actually. It's a clock division by 6. So in clock division by 6 you can see that this output will keep on repeating itself. So you will see that after it will go 0, 1, 2, 3, 4, 5. So when the output is going to be 5, so these output will keep on repeating itself. That means um, if I take Q2 as my clock divisions, then I can see that my Q2 is actually a clock divided by 6, because 4 times it will return 0 and 2 times it will return 1. So which means that duty cycle is going to be a 1/3. So for 1/3 of the time it is going to be 1, and for 2/3 of the time it is going to be 0. And but because this is going to repeat again and again, this could be a clock division by 6. So in this way, if we use these modulo counters, these modulo counters can help us in dividing the clock by any particular number. It need not to be 2's to power number. So let's say if I want to design a clock divider by 1000, so I can design it accordingly. So I can, although the duty cycle will not be 50%, but we would be able to design a clock divider by any particular number. Yes, so this may also be worth saying here that clock division is easier to be done using digital circuits, essentially using flip-flops, but clock multiplication, let's say the input clock period is 100 megahertz. So there is no method, no clear method or no systematic method that can help us in achieving a clock which is of 200 megahertz, or a clock which is faster. So from 100 megahertz we can go down to a slower clock, but faster clock will not be possible. And in creating a slower clock, we can be we can calibrate, or we can basically do any, we can divide by any particular number of our choice. Okay, so now one last application, related application here could be, we can essentially use this particular method to generate any sequence. Any sequence means that let's say I would like to have this is the example I'm taking. So for example, initially the value is 0, then I would like to, in the next clock cycle I want to make it 2, and then 1, then 4, then 6, then 3, then 0. So and then this can keep on repeating. So similarly, any sequence of numbers, if I would like to generate, then that could be generated. Then whatever is the next number I would like it to be in the next clock cycle, according to that I can write my next state equations, and based on those state equations we can find out what would be the we can design our logic so that the next number would be equal to whatever sequence we would like to write. What would be the steps here? What would be the method? So basically, let's say first of all we need to find out how many bits would be there. So for example, in this case it would require 3 bits, but any sequence of numbers, then whatever is the maximum number, log of log 2 of that particular maximum number can tell us the number of bits um, in that sequence generator. Whatever is the number of bits, that many number of flip-flops memory elements we require. Now after that we can write a truth table. In the truth table we can write, let's say the present state is 0, then we can say the next state is 2. If the present state is 2, next state is 1. Similarly, the present state is 1, the next state is 4. So for all the transitions we write present state and the next state. And for each next state bit, so here for example there would be 3 bits. For each next state bit we can write a boolean expression, and that boolean expression could be assigned to input d input of that particular flip-flop. So and d would be transferred to q at the positive edge of the clock. So that means this sequence generator, any sequence generator can be designed using D flip-flop. So with this, I would like to close this lecture. And in summary, what we have seen in this lecture, that we can use these D flip-flops to design any other flip-flop like JK flip-flop or T flip-flop, etc. Okay, and we have also seen how these D flip-flops can be used to design a clock divider. We have seen both clock divider which is synchronous and another clock divider which is asynchronous. Similarly, we can use this D flip-flop to design counters also. Counters could be synchronous or asynchronous. In case of asynchronous counters, the output of one D flip-flop is given as the input, clock input of the next flip-flop. But in case of a synchronous counters, we do not modify the clock because the clock is my synchronizing signal. Okay, so and value of d is calculated based on a truth table. So that is how we can design synchronous counters. And using the similar technique, the way we have designed synchronous counters, we can also design modulo counters. We can also design any kind of a sequence generator where sequence is some integer number, and from one integer number we would like to go to another integer number. So that kind of a sequence generator can be designed using D flip-flop. So with this I would close. Thank you very much.